After we've seen the definition of the Riemann integral and I've seen the Riemann integrability of certain classes of functions, it's now time to study the properties of the Riemann integral, namely kind of its compatibility with addition, multiplication and so on, and to really work out kind of how the Riemann integral behaves when we want to do computations with it. In this section I will not do all proofs in detail, as you will see, because they are quite tedious actually and not that instructive. It's a bit like bookkeeping. You have to do this, but it's not very exciting, so I will leave most of the proofs to lecture notes and only discuss some aspects with you. Okay, in the first theorem I basically summarize all properties of compatibility of the Riemann integral with algebraic operations. This is theorem 511, which has a lot of parts. So assume we have A, B, and R with A smaller than B, and assume that we have two Riemann integrable functions, which we denoted by this curly R. So F and G are Riemann integrable on AB. Then the following properties hold. The sum of the two functions, f plus g, is again Riemann integrable. Okay, it's not very surprising, but still we need to check this. And the good thing is the integral behaves nicely with respect to sums. The integral of f plus g of x dx is the sum of the two integrals. A to b f of x dx plus the integral g of x dx. Sorry for squeezing, but I hope you'll be able to recognize. So this is simple. So if we can always integrate sums of functions by integrating the different summands individually. Okay, next thing, the multiplication with constants. If we take lambda times f for some constant lambda, another Greek letter I'm now going to mutilate. Okay, I hope so Greek letter lambda. Is again Riemann integrable, where lambda is some constant, so this is true for all lambda in R. Oops, okay. And here the integral also behaves nicely, namely the integral from a to b of lambda f of x dx is simply lambda times the integral from a to b f of x dx. So multiplication with constants also doesn't matter. You can just pull them out of integrals. And this is something, if you did integrals in high school, this is kind of totally natural for you. And this looks totally obvious kind of in that sense if you have already the connection of integrals and derivatives, but which we will see in the next section. But so far you of course need to show this with upper sums, lower sums, and so on, in general case. Okay, next thing, and this is also something when you think about that the integral is somehow measuring the surface below a graph, so intuitively, this also makes sense. Namely, if f of x is smaller than or equal to g of x for all x in the domain AB, then the integral of f of x is smaller than or equal to the integral from a to b g of x dx. Okay. Now another thing, and if you think about the definition and about the idea, this is something which looks also pretty obvious. If we take some number c, which lies somewhere between a and b, so in the open interval from a to b, then the integral of a to b f of x dx is the same as the sum of the integrals that we get if we first go from a to c, f of x dx, plus then going from c to b, f of x dx. So we can kind of decompose the intervals in two intervals or several ones. Of course we can iterate this formula and use this multiple times. So we can just always split up the interval into shorter intervals and integrate them separately, which in some cases is really a useful property. So we can, and this is something, if you think about the surface area, this makes perfect sense intuitively. Then E, assume we have some numbers small m and large m in R, such that m is a lower bound for f and capital M is an upper bound for f, so f is between these two numbers for all x in A, B, then And of course, we can always find such numbers because recall by definition a Riemann-integrable function is always bounded. So if we have these numbers, if we have these bounds, then m times the integral going from a to b f of x, nonsense, m times b minus a is smaller than the integral of from a to b of f of x dx, and this in turn is smaller than capital M times b minus a. And this is something also that makes perfect sense if I draw you a picture. Of course, a picture is not a proof, but just intuitively. So we have some function from a to b, whatever. Okay, now if we have some number small m, which is the lower bound. So let's say we take a good lower bound. So here we have m, and so maybe let's modify my image so I can draw it better. Okay, like this. So here we would have some capital M, which is an upper bound. Okay, and recall we want the surface area below the graph. So the thing on the left, in the left-hand side of these inequalities, so this term here, this is the surface area of this rectangle, which has height m and length b minus a. So b minus a is length of this. So this yellow rectangle here, this is the area of this rectangle, this is what's here, and this is obviously less than the graph. I mean, this is something like a very, very, very simple lower sum by just taking the partition to be a and b, and the same thing on the right-hand side, and this is basically how you can also prove this. And if you take a look on the right-hand side, analogously, so if m is there, we get this pink rectangle here, and of course the area of this pink rectangle, excluding this line, the surface area of this rectangle, of course, this is bigger than or equal to the graph. Okay, so on to the proofs. I will only do the proof of part A and also only a part of it, because this is kind of, it's kind of not very, as I said, not very interesting and not very illuminating, so to say. So part A, but how do you approach these things in general? And as you will see, if you take a look at the lecture notes, the other parts are, the spirit of proof is always the same by using these lower and upper sums in a smart way and using their properties. So first of all, we take a fixed partition. P from x0 to xn be a partition of AB. Okay, and now with respect to this fixed partition, we want to think about upper and lower sums of f of g and of f plus g. Okay, what do we know there? First of all, we want to discuss the properties of supremum and infimum, because they appear in the lower and upper sums. Let's fix some number j between 0 and n minus 1. Then we get the following important inequalities. So the supremum of x between xj and xj plus 1, so just some arbitrary interval, of f plus g of x. This is a term that pops up in the upper sum of f plus g with respect to the partition P. This is, so just by writing this, more explicitly, it's the supremum of this expression here. Okay, and now we want to make this very big, but we always have to take the same x in both variables. And so if, I could now really explicitly work a bit more with suprema, but I just want to do this vaguely or roughly because this is fine enough. Of course, if I take the same, the supremum of this expression will be smaller than or equal to, I could get something bigger if I would allow both variables to vary. So if I just wanted to maximize the expression f of x plus g of y for some y in the same interval. So this is the sum lower than or equal to, and this is now this expression that does precisely what I just said. The supremum of x in xj plus 1 f of x plus, and now taken separately, the supremum from xj to xj plus 1 g of x. And now to compute the supremum, we can, we could have different values here. This is kind of something, I mean, this is not really a proof, I'm a bit hand-waving here, but this is enough for, because I don't want to go into messy details with supremum at this point. And analogously, you can also make the following argument. If we take the infimum of x between xj and xj plus 1 of f plus g of x. Then, by the same argument, the infimum is making it as small as we can. And of course, if we do these two individually, this might become smaller than just taking this expression where we would take the same variable in both functions. So this is bigger than or equal to the infimum over x in xj, xj plus 1, f of x plus the infimum of for x in xj, xj plus 1, g of x. Okay, this is yeah, something I would ask you to think about for yourself and maybe to formally prove this if you want to try a bit with supremum and so on. And one derives from these inequalities. If we just apply this to the definition of lower and upper sums, I mean the only difference between the lower and upper sums of different functions is that we have the supremum of the functions there. And this means that in our situation, one derives from these inequalities the following. This is what I want to call star, as I want to refer to this later on. U of f plus g with respect to the partition P. Now, we've seen that this now contains these expressions here, the supremum of f plus g of x. And we have seen that we can then estimate this by this. And if we just kind of play around with the upper sums, we see that it directly follows that this is smaller than the sum of the upper sums of f and g, simply by using this supremum property. And in the same way, we can use this infimum inequality that I've given here to show that the lower sum of f plus g with respect to p is bigger than or equal to the sum of these two lower sums. So with star, I want to denote both of these equations, both of these inequalities, to be precise. Okay, now let's work with these lower and upper sums. We know that f and g are Riemann-integrable, that's the assumption. So, by this criterion for integrability, theorem 5.7 that we've seen previously, we can find partitions P1, P2, partitions of A, B. I forgot one tiny bit. We choose a fixed epsilon bigger than 0. And of course, we want to then use this integrability criterion to show that we can find a partition such that the difference of these two, the upper sum and the lower sum of f plus g, with respect to that partition is smaller than epsilon. So by now using this in the other way around, these are Riemann integrable. So with respect to that epsilon, we can find P1 and P2 such that the upper sum of f with respect to P minus the lower sum of f with respect to P is smaller than epsilon over 2. Again, I will then do some computations where it nicely works out to have an epsilon in there. This is smaller than epsilon over 2, and the same way, P1. In the same way, we get that some P2 such that the upper sum of G with respect to P2 minus the lower sum of G with respect to P2, that this guy is smaller than epsilon over 2. Okay, so what do we do with this? We do what we always do when we have two partitions. We choose a common refinement. So we take P0 to be a common refinement, common refinement of both partitions. And it turns out that this partition is now enough to ensure the same, or the beautiful property here, or the important property that we need for the function f plus g. And this we shall see after I erase. Now that we've got the common refinement, we have everything we need and just need to put things together in the right order. Namely, we get that u of f plus g with respect to P0, so the upper sum, minus the lower sum of f plus g with respect to P0. So by the previous computations about lower and upper sums, so this was star, we get that this one is smaller than or equal to u of f P0 now plus u of g P0. I'm just reordering the terms. And now this is then, since there's a minus sign, this is smaller than minus L of f minus L of g. So we can just put this here into place, f P0 plus this minus LG P0. And now since P0 is a refinement, we've now seen the properties of refinements. This was theorem 5, 2, that this is smaller than or equal to u of f p1 minus L of f p1 plus u of g p2 minus L of g p2, and there we've just chosen these partitions such that this is smaller than epsilon over 2 and that this is smaller than epsilon over 2, so this is smaller than epsilon. Epsilon was an arbitrary number, and so we get by this criterion for integrability that we can always find a partition with this property. So by theorem 5.7, f plus g is Riemann-integrable. Okay, and now by a similar computation using these properties, you can also show that, I won't do that the integral is really the sum of the integrals, but I won't do this here because it's really not that exciting. So the rest of the proof, so the rest of part A and of parts B to E is contained in the lecture notes. But you see it's always kind of lecture notes. You have kind of choose your partitions wisely, do some computations about lower and upper sums, and then use this criterion. It's mostly always this criterion theorem 5.7 with which you have to kind of choose, use in a smart way. Okay, there's one thing that was not part of this proof, namely the composition. And it turns out that if you take two Riemann-integrable functions, there are really examples for which the composition is not Riemann-integrable. So there it doesn't work as nicely as we want. But I won't discuss the examples because they are really complicated. So there are examples, they are not beautiful, but there are. So what do we know about compositions? There's one situation in which we directly can say that the composition is again Riemann-integrable, namely if we demand a bit more. So theorem 5.12, start on the next blackboard because I don't have that much space here. Theorem 5.12. So again, so that I be some interval f from in interval AB, again A smaller than B, I don't write this down this time again, this to be Riemann-integrable, and such that this interval I is chosen such that the image of f, so f of the whole interval AB, is contained in the interval I. And now we take a second function, g from I to R, which we want to compose it. And as I said, if g is just Riemann-integrable, it doesn't follow that the composition is Riemann-integrable. But we need to assume here that g is continuous. This is enough. So the composition of a continuous function with a Riemann-integrable function is Riemann-integrable. Then, so g composed with f, which is now going from A, B to R, is Riemann-integrable. Okay, the proof of this theorem is not that easy actually, so it's a bit technical, and I will kind of go quickly through this to give you the main idea of how to prove this. I've written down it with a bit more detail in the lecture notes. I hope that it should be then understandable if this is now too fast for you. Okay, first of all, we have assumed that f is Riemann-integrable. Riemann-integrable functions are bounded, so we can assume that I is a bounded interval. We can always restrict this such that this has this property. And we can always restrict to a compact interval. So we can just assume simply that I is a compact interval. This doesn't change because we always have that this is part of a compact interval, and we may just restrict to some sufficiently small compact interval to get this computation. So assume, without loss of generality, that I is compact. I don't write down this line of argument. That I is compact. Now, as I said in the lecture notes, there's a more detailed version. We've had this before in the proof of a theorem. The number I don't recall. That we can now use the uniform continuity. Namely, this is a continuous function on a compact interval now by assumption. So it's uniformly continuous. And so, as before, I haven't written down which proof it was on which we made this argument. We can use this uniform continuity of G and show that for each epsilon bigger than 0, there exists some delta bigger than 0, such that g of x minus g of y is smaller than, and this time we want epsilon divided by 2b minus a. So this is something that we'll then figure out that this is the right notion in the end. That this holds for all x and y in I which have distance smaller than delta. Okay, and this is now also again denoted by star this time. Okay, this is what we get from the uniform continuity. Now, we define C to be the supremum over all x in I of g of x to the absolute value, and we know that this is a continuous function under compact intervals. It has a maximum and a minimums. In other words, it is bounded, especially. So we know that this must be smaller than infinity. So this is indeed a real number that we're talking about. Yeah, so this is since g is continuous. So we can assume that g is non-trivial, that g is not the zero function, because if it was the zero function, this would be pretty obvious because the composition would be zero. And if it's not the zero function, we can assume that c is bigger than zero, because if anything happens, this will increase the value of c. And we assume without loss of generality. So, sorry, at this point I should have mentioned, we put this and we fix the value of epsilon this time. And we want to show that for some fixed epsilon, we can show that is integrable by a nice property, by the lower and upper sums, as we shall see. So we assume that c is bigger than zero, and without loss of generality, that if we take for this epsilon, this number delta, of course, if we have delta somehow given that it has this property, we can always make delta smaller and preserve this property. So we can assume without loss of generality that delta is so small that delta is smaller than epsilon divided by 4c. Okay, this inequality I denote by double star. And we shall see in a bit why this is, why we need this. It's basically at the moment you can't see why this happens. It's only because the computation then works out magically like we want it to. Okay, now we take, for this epsilon, we take a partition P in the partition P is again, I want to note the entries as we always do by x0, x1 to xn. So this is a partition of AB. So given this partition, we want to define it in such a way that u of fp minus L of fp, so f is by assumption Riemann-integrable, so we can kind of for each small number we can find a partition such that this difference is arbitrarily small, and we want it to be so small that it's smaller than delta squared. Again, we will see later on, it's only, we do this because it turns out that this then works out nicely. Now, we want to shorten our notation a bit. I want to denote capital Mj to be the supremum of x between xj and xj plus 1 f of x. So this is one of the numbers that appears in the upper sum of f with respect to p. And I want to define another number, mj star. And mj star should be, again, a supremum, but this time I want to consider G composed F. So the supremum of this composition, which appears, of course, in the upper sum with respect to P of G composed with F. The same I want to do for the infima. So Mj, small mj, should be denoted by, should denote the infimum of x between xj, xj plus 1, f of x, and small mj star is then the infimum of G composed with f of x. Okay, so what we're interested in to show the integrability later on is of course the difference between these capital Mj star and small mj star. This is what appears in the difference of the upper and lower sum of the composition, and this is what we kind of need to get to become very small. And to do so, we will use some little tricks here. So then, first of all, this looks very mysterious, but we will see how it all falls into place. We now, first of all, the indices j, they go between 0 and n-1, and we want to split them into two groups. One that has a nice property, one that is not that nice, but still we will have to treat them differently. First of all, we let A be the set of all indices, sorry, n-1, such that mj minus small mj is smaller than delta. So the sup and the inf. This doesn't, of course, this doesn't have to be the case for all j, because like in the upper sum we could have the interval could be so small such that even if this difference is big, if we take the products again later, the difference of the upper and the lower sum will be very small. Not that important for now, and we take B to be the complement of this set. So the set where these differences are always bigger than or equal to delta. So the set 0 to n-1 without A. Okay, and now we want to treat the different components of the upper and the lower sum differently for these two cases. Namely, we do the following. First of all, for j in the set A, where these differences are indeed that small, we get the following. We get that mj star minus small mj star, which we kind of want to, we hope to be a small number. This is this is smaller than or equal to, just by definition, the supremum over all x and y in xj plus 1. And this is, if you play around with sup and inf, you will see that, so this is the supremum of the composition on the interval, and this is the infimum. And you can rewrite this as the supremum of f of g of x, f of g of x minus other way around, I'm sorry, g of f of x minus g of f of y. Sorry, I just said something wrong. Here we saw that the difference, that by construction of A, the difference of the supremum and the infimum is smaller than delta. But this means that any two values of f in this interval, the difference of them is smaller than delta. So this means that f of x minus f of y, these 2 points are delta close to each other. Their difference here is smaller than delta. But then, now this comes into play, because now the arguments here, this time it's f of x and f of y, don't let yourself get distracted by that. They are closer than delta to each other, so this holds. We can use this inequality. So by inequality star, this is smaller than epsilon over 2b minus a. Which means, if we now take the components of the upper sum, the difference of lower and upper sum which belong to A, so I mean the sum over all j in A, mj star minus small mj star, I will now write down the relation to the lower and upper sums later more precisely, times xj plus 1 minus xj. So this is really part of this difference of upper and lower sum. By this inequality, this is smaller than epsilon over 2b minus a, since each of these factors here can be estimated, and we can pull this out of the sum, times j, the sum over all j and a of xj plus 1 minus xj. But we know that these are kind of lengths of these intervals which are part of b minus a, so we know that the total length of these intervals, which is this sum here, is at most b minus a. So this is smaller than epsilon over 2b minus a times b minus a, and of course these cancel each other, and so what we've shown is that the supremum, the sum over j and a of capital mj star minus small mj star xj plus 1 minus xj is small, is very small, it's smaller than epsilon over 2. So this part of the difference of lower and upper sum is small. What remains to be shown is that the other part of the difference of lower and upper sum, namely the sum over j and b of this expression, is again small. And this we will do in the, after erasing. In the case of j and b, we start with a computation which a priori doesn't involve these numbers mj star and small mj star, but we make a kind of intermediate step, namely the following. We think about the sum of j in B of mj minus small mj times xj plus 1 minus xj, which is part of the difference of upper and lower sum of the function f. So this is then smaller than or equal to u of fp minus L of fp, but by assumption, we've just, the choice of p was given such that this is smaller than delta squared. What does this help us? We have seen that this expression here, so just by definition of b, this means that all these differences here are bigger than or equal to delta. So we can estimate the sum from below by just taking the sum of j in b, xj, need a bit more space here. Sorry about messing up here. Maybe add some water, more fun. Sorry about that. Okay, so for j and b, let's write this a bit smaller. So we can estimate this from below by delta. So this means delta times the sum of all j in b xj plus 1 minus xj smaller than smaller than delta squared. So we can just, since delta is a positive number, we can just divide everything by delta and preserve the inequality. So this means that the sum over all j and b of these differences here minus xj is smaller than delta. So kind of the total contribution of this part of the parts of the interval which are part of this partition where these differences become quite big, there we know that this difference has to be small, that this total length has to be small. Okay, now we need one more assumption which you have to believe me at this point. There's also something that you can check and it's in the lecture notes, that the difference mj upper star minus mj small mj star, which appears in this difference, that this kind of a value of f minus some other, value of the composition minus some other value of the composition. But it turns out that this is easy to see that this is smaller than or equal to twice times c, which was the supremum of g on this interval. So this is g of something, this is g of something, and just by standard estimates with the absolute value, you can show that this is smaller than or equal to the supremum, twice the supremum of the absolute value, because this, the value of this is smaller than c, and this is smaller than c, and so we're done. So this gives you this particular simple estimate. So, given this estimate, we take now the difference of lower and upper sums, or the part of this which belongs to b, that we want to make small. So capital mj star minus small mj star times xj plus 1 minus xj. This is the guy that we want to be small. Now, by this estimate, this is smaller than 2c times the sum of j in b xj plus 1 minus xj, but this sum we've just estimated here, so this is smaller than 2c times delta, but just by a choice of delta, I have made the assumption that delta is so small that this is smaller than epsilon. This was the estimate double star. It's smaller than epsilon over 2. The estimate was that delta is smaller than epsilon divided by 4c. So this then makes this work as well, and so this means that we have now finally our estimate. Namely, this implies that u of g composed with fp minus L of g composed with fp, and I kind of leave out the details, but as we see, this now consists of all these differences, of all these terms here, the sum of all of these for all j between 0 and minus 1, and since this is split into a and b, we get that this difference here is, so this is the sum of all, I need more space, sorry. This is the sum of all j in a, mj star minus small mj star, xj plus 1 minus xj, and the remaining are the ones who are in b. So sum about the same thing, mj star minus small mj star, xj plus 1 minus xj, and we've just shown in these two parts that both of these sums are smaller than epsilon over 2. And of course, this is epsilon. And since epsilon was arbitrary, this is our criterion for integrability. So we have, for this epsilon, we found a partition with a lot of effort, I must admit, but we found a partition such that this difference is smaller than epsilon, and so we're done. So by theorem 5.7 again, G composed with F is Riemann-integrable. Okay, this was work. But it turns out that we can use this theorem to get some more concise results about integrability, which now basically follow straight away. Okay, theorem 5.13. So again, we take an interval AB where A is smaller than B, and we take two Riemann-integrable functions on that interval. Then we get two beautiful consequences. First of all, A, and this is also something that was not part of the previous theorem with the different algebraic properties, the product of Riemann-integrable functions is again a Riemann-integrable, which is good. I mean, this shows that kind of with our algebraic playing around, we always remain integrable and don't need to worry about this. Part B is now that the absolute value of a function is also Riemann-integrable. The absolute value is in the class of Riemann-integrable function, and there holds a nice inequality. The absolute value of the integral of f is smaller than or equal to the integral over the absolute value of f. This inequality is sometimes also called the triangle inequality for the integral. So just keep in mind, if you read about this triangle inequality for integrals, it's usually this inequality that's considered. Now, how does this follow from the previous work? We just have to kind of write these expressions. So first the product and then the absolute value as special cases of the thing we did before. So as the composition of a Riemann-integrable function and a continuous function. In case A, in part A, we start with the case f equal to g, so the integral of f squared. Now, this is really what we had before. So we take f squared, which is f times f. Then it follows, the claim follows from the previous theorem. Theorem 5.12. Since we can write f squared as phi composed with f, where phi is simply the function phi of x is x squared. And this is just simply by first taking f and then squaring. This is what is f squared. So by the previous theorem, we immediately get, since this is obviously continuous, we get that this is Riemann-integrable. So we now know that squares of functions are Riemann-integrable, and now we're almost done. Because for the general case, we now use this property. So we have two functions f and g, and now we make a little computation. The product of f plus g with itself, this is now can be treated in the same way as we were kind of computing in the field because of these associativity and distributivity results that are involved. This is the same as f squared plus 2 times f times g plus g squared. And if you just resolve this equation by f times g, this means that f times g is 1/2 f plus g squared minus f squared minus g squared. Okay, no one in the right mind would use this formulation to describe a product, but we're done. Because these are all squares. This is Riemann-integrable, this is Riemann-integrable, this is Riemann-integrable, and we have seen that multiplication with constants and here addition and or subtraction then, they lead again to Riemann-integrable functions. So here we directly get that, so by combining theorem 5.11 and previous observation, so the observation that squares are Riemann-integrable, it follows that f times g is Riemann-integrable. Okay. For part B, it's a similar argument. Namely, basically the same, because we can say the absolute value of a function f is the same as phi composed with f, where phi of x is the absolute value of x, and we know that the absolute value is continuous. We've seen this before, so this is again a composition of a continuous function and a Riemann-integrable function. So it directly follows from theorem 512 that f to the absolute value is Riemann-integrable. Now, for this inequality that we need to show, this is also not that difficult. We just introduce in some notation, we let C be a number which is either 1 or minus 1, and we let it be 1 if the integral of f is positive or non-negative. A to b f of x dx is bigger than or equal to 0. Minus 1 if this integral is negative. Okay, then let me see if I can fit this in right here. The absolute value of the integral is then, just by definition of the absolute value, the same as c times the integral. Okay, we know that multiplication by constants is, we can just pull them inside the integral. So this is the same as the integral from a to b of c times f of x. This is theorem 511, part b. And so integral of c times f of x. And now this is either f or minus f. But we know that both f and minus f are smaller than or equal to the absolute value. And we've seen, that was also part of 511, if we have two functions and one is bigger than or equal to the other always, then the integrals get this property. That's kind of called the monotonicity of integrals. So this is then by, again, theorem 511. Which part was this? I haven't written this down actually, but theorem 511, this is smaller than or equal to integral of the absolute value, simply because there's this inequality between these two functions over which we integrate. Okay, this concludes this proof. Okay, let me erase. One more remark on the previous theorem. We've seen that products of Riemann-integrable functions are always Riemann-integrable, but what we don't have is a particular rule of how the integrals are related. Like for derivatives, we had the product rule, so we could always kind of compute the derivative of a product with respect to the other derivatives. With integrals, it's not that easy because it requires a bit more work. So in general, note that, so in general, let's say a priori, there's no relation in general between the integral of the product f of x g of x dx, so between these values here, the integral of f and the integral of g. So it's a bit more complicated than in the setting of derivatives, where we could really just compute everything. Every derivative of a product is no problem. Here it's a bit messier. So we will, in the next section, we will learn the technique of integration by parts, which not works for every Riemann-integrable functions, but only for some, basically, as we shall see. And then kind of how to compute integrals of products. But it turns out that this is really not as simple as in the derivative case. Okay, there's one more theorem in this section. The same as for derivatives, there is a mean value theorem. Which in philosophy is similar to the previous mean value theorem, and this is called the mean value theorem for integrals. Actually, this is often called the first mean value theorem for integrals, since there is a second one, but I will not discuss the second one here because this is not too important for us. This first mean value theorem, which I will just call mean value theorem, is enough. And this theorem says the following. So assume we have, assume we have a function phi, which is Riemann integrable, again, on some interval a, b. I don't write this down every single time. And assume that the function is non-negative. Okay, then, if we have a continuous function on the interval, so f from a, b to r continuous, assume we have these given. There always exists some number xi in the interval AB such that the following relation holds. The integral from a to b of the product f of x times phi of x dx is the same as f of xi times the integral from a to b of phi of x dx. Okay, we can always factorize out such a f at the point by this as the product with the simpler integral. Okay, let's prove this theorem. And it turns out we will use a beloved theorem of ours from chapter 3 in the process. So, first of all, we have just seen that the product f times phi is Riemann-integrable, so this left-hand side is already defined. So by theorem 513a, f times phi is in the set of Riemann-integrable functions on AB, so it's well defined. Just to note this, so f is continuous, AB is a compact interval, so by a theorem from chapter 3, that was theorem 332, f has minimum and maximum. Theorem 332, f has a minimum and a maximum. This minimum we call small m, and a maximum which we call large M. And so by theorem 511, by these algebraic properties, and there we need part B and part E to combine this. We've seen that, so first of all, sorry, I was confused for a bit. M times the integral of phi of x dx. So if we just multiply it with the minimum of f, this is, of course, this is part B of theorem 511, the integral from a to b of small m times phi of x dx. And we know just by construction as a minimum that this is smaller than the product of f of phi. And because of this monotonicity property of the integral, which was there part E, should it be then? I'm not exactly sure. Am I right? Let me look it up. Yes, part C. Just confused. B and C, sorry. This is this monotonicity property of the integral. So we get f of x, phi of x dx. But now again, this monotonicity, we can also bound this from above by the integral of m times, so large M, the maximum, times phi of x dx, which is of course the same as m times the integral of phi of x dx. Okay, so this is just some lengthy computation, it's a bit tedious, but we see that the value of this is somewhere between m times this and large M times this. So small m and large M times this. This lies in between there. So this means, in particular, we can find some number, there exists some number mu in the interval from small m to capital M, such that the integral f of x phi of x dx, integral from AB, is mu times the integral of phi of x dx. Okay, by the way, we needed the non-negativity, so the fact that phi is always greater than or equal to 0 to get these inequalities here. Because otherwise, if the function would be negative and we would multiply with a positive constant, the inequalities would go other way around and so on. So this is only in this situation needed. So we have this between these two values, so there is some mu, such that this is mu times this. But now, small m and large m are the minimum and the maximum, so these are indeed values of f. So since these are values of f, we can use the intermediate value theorem. By the intermediate value theorem, every value between small m and large m is also a value of f. By the intermediate value theorem, This has to be a value of f, so there exists some psi in the interval AB with f of psi is equal to mu. Done. This is all we needed. Okay, this gives us the mean value theorem for integrals. Just one final remark, one corollary and then one remark. There's one special case which looks particularly interesting, or which is kind of the interesting idea. So let f be a continuous map on the interval AB, from AB to R be continuous. Then there exists a psi between A and B, with the integral of f of x dx is f of psi times b minus a. Okay, and this is a direct consequence of the previous theorem. Corollary 516. Forgot the number. We simply need to apply the mean value theorem for integrals. And we just have to take a particular function phi. We just take phi of x constant equal to 1. Then the integral over phi, integral over 1 is just the difference of the two bounds, so b minus a. So then we precisely get this notion here. And this is geometrically interesting. Let me maybe draw a little graph somewhere in here. So very simple. So again, assume we have some function here which goes like this. So the integral, as I've said many, many times before, is the area of the surface here is the idea. And now this here is the area of a rectangle of length b minus a and height f of psi. And this means there is some psi that's somewhere here, and let's say somewhere, I don't know, here would be the psi, and here would be f of psi. No, this is not correct. This is too high, sorry. Maybe here, and then psi would be somewhere there, such that if I take the rectangle, let me just color chalk. If I take the rectangle at this height here, whoops. Okay, this is not really correct, but that the area of this rectangle is the same as the area below the graph. So here some bits are missing, but here some bits are missing in the other direction, so this cancels each other out. So we can always find some value in between such that this rectangle at that height has the same surface area as the area below the graph. And one final remark is that these quantities are kind of quite important also for their own interest, or that these the things appearing in that corollary. First of all, we have some Riemann-integrable function f on AB, on this interval AB, and we put the following. We say m of f we define as 1 over b minus a times the integral of f. Okay, so the previous theorem here, the previous corollary just says that there is, if f is continuous, there is some value psi such that this is then the value of psi, value of f xi. But this quantity here is called the mean of f. And this is now really interesting because this generalizes kind of the average we know. We have seen the arithmetic mean of numbers and the geometric mean of numbers. And this here kind of generalizes the arithmetic mean. With the arithmetic mean, we sum up finitely many things, and this is kind of seen like an infinite analog of this. So the average value that f takes on the interval AB, it's this quantity. This is kind of what you can see. There's also a nice video by 3 Blue 1 Brown, which I may post in the comments if I think of it, where this is really nicely explained how this is really a mean. So, but this can, in this way you can compute the average that a function has. So for example, if f is some temperature function, which is kind of giving the temperature at a point over the course of the day, then this value here would be the average temperature that you had in that day over a full day, for example. And the same, you can do a similar thing, that phi be Riemann-integrable with phi of x bigger than or equal to 0 for all x in AB. Then the quantity m index phi of f, and this is now defined as the integral from a to b of f of x times phi of x dx divided by the integral ab of phi of x dx. This is called the weighted mean. So phi is seen as a weight. I will explain this in a bit. The weighted mean of f with respect to phi. Okay, and this is now seen as also an averaging procedure, but this time, so this is now almost the two sides of the mean value theorem for integrals. Oops. Oh no, here. Okay, so if we divide by this here, and phi is non-zero. Sorry, otherwise the denominator would be 0. A bit more, sorry. We need to assume that this integral is non-zero. I don't write this down explicitly. I just want to give you the main idea. So this would be kind of almost the quotient of the sides of the mean value theorem. This is also kind of average, but now this kind of phi now steers the average in the sense that phi tells us where the priorities are over which we want to average. For example, this appears a lot, like for example then in quantum physics, where phi is some probability distribution. This kind of tells us how probabilities are, how kind of what outcomes of certain events are more likely than others, and we want kind of to put an emphasis on the values of f at these things, and so you can use these weight functions to stress a certain part of it to get some, to steer this average in a bit. So this maybe you will probably see in your course on quantum mechanics at some point. But this is kind of the idea of how you can kind of modify these averages by making some priorities of which parts of the interval are more interesting for you, and this is then expressed by these functions phi. Okay, this is all for what I want to tell you about the properties here. In the next section, it will become a bit more lucid, I think, because we now explore the relation between differentiation and integrals, and we will see that this gives rise to a lot of new computations and better computations than before. See you in the next section.